discussing one-dimensional unconstrained optimization techniques, and in last session we have talked about golden section search method. It was an improvement over the random search method we have discussed earlier. The improvement is basically from the fact that now we have a more methodical way of looking for the minimum or maximum, while in random search we were simply searching randomly as the name suggests. Now we will move forward, and in this lecture we will talk about Newton-Raphson method. Now Newton-Raphson method, you are already familiar to it from our discussion in root finding, and here you will see that method is just like that. And still we'll be discussing this method because this will open up a new horizon in optimization. We'll use this kind of horizon in optimizing multidimensional unconstrained problems. So let us see what we do in Newton-Raphson method of optimization. In Newton-Raphson method, we are optimizing here, in fact minimizing this y equals fx function, and our goal is to find this x star that will minimize this fx. We start with an initial guess of x naught. Now the idea here is to search for this x star, but search taking help from the derivative here. So let us see what it is. What we do here to update this x naught, we go up to x1 and we add this h naught d naught with this x naught. So from here we have come up to here. The difference between these 2 points is h naught d naught. So h naught is the descent direction, that is which direction we are coming down. We are on this function and we are coming down toward the minimum. So which direction we will go? Well, in this case we are here, so we can only go either right side or left side. We have to pick one direction, either right or left. So which direction we have to think about it, and then how long we'll go. This distance, how far we'll go, that gives us the step size. So we have these two parameters here. One is descent direction, or we also call search direction, travel direction. And the second parameter is step size. Step size is always positive and a scalar. The direction will be given by this d. H is always positive scalar. Okay. D in this case, it is not really a vector. It is only left or right. But even you can think of it as a vector in positive x or negative x direction. But in multidimensional case, it will be clear that it is indeed a vector. So let us see now. Here, how do I decide this direction, left side or right side, which direction I'll go? To do so, we take help from the derivative of that function at this point x naught. If I take the derivative, means I take the tangent and I essentially look at this angle. That's what the derivative means geometrically. If my derivative is greater than 0, that tells me that if I go in x direction, my y increases. That is the derivative greater than 0 means. So therefore, if I go in right side or in the direction of increasing x, it probably will not go toward the minimum. So we want to take the reverse direction. So the descent direction then in that case should be left. So if my f prime x is greater than 0, I'll take the left. And similarly, if my f prime is less than 0, then I know that when x increases, then fx decreases. So then I'll go to the right. That means my x1 will be greater than x0. Now we can sum up these two ideas simply taking this descent direction to be negative of the gradient. If gradient is positive, then x1 is less than x0. If gradient is negative, x1 is greater than x0. Therefore, my descent direction is negative of gradient. Now, with this descent direction that we have decided that it will be negative of gradient at this point, I want to figure out that, well, I will go this side, but how far I will go? That I have to find it out. So for that, I need to know this step size. And to find this step size, we assume that, well, at x equals x0, we are not at minimum because my f prime x0 is not equal to 0. If it is equal to 0, f prime x0, then I am already at minimum. I don't have to do anything. But if it is not 0, then I have to find a step size. So what I am assuming here is that, well, if I take a step, I'll probably minimize fx. And that may be true if I am very, very close to this minimum point. So that is where actually when you come to closer and closer to minimum point, this Newton's method works really very well. So here we hope that in next step we'll minimize this fx. That means f prime at x equals x1 will be 0. At this step, f will be minimized. Therefore, we can take this f prime as x equals x0 as 0, and I can write that as x0, that is as 0th iteration, plus h0 d0, and I can expand it in Taylor series. Once I expand, I have the first term is, because I am expanding this f prime, so first term is f prime x0, then this h0 d0, f double prime x0, etc., etc. We neglect the higher order terms from here, and we find out this h0. My h0, because it is 0 here, I can take this f prime other side and divide by f double prime. So this will give me h0, f prime divided by d0, f double prime, and d0 we already know that d0 is in fact negative f prime. So my h0 comes 1 by f double prime. Therefore, looking at the basic algorithm, my x1 is x0 plus h0 d0. It will come as x1 equals x0 minus f prime divided by f double prime. This f prime by f double prime is calculated at x0. So everything about the left hand side is known. That is how Newton-Raphson works. But we need to know the f prime and f double prime of the function. And indeed, the function must have f prime and f double prime. If the function doesn't have these derivatives, then we cannot use this method. The way we have found this h, and there are many more ways like this of finding h in different methods, which we'll talk later on. But this finding h, or an acceptable step size, not necessarily always optimum, but an acceptable step size, this is a method we call line search. And line search is a family of method. This is not one method that we have just seen here. This type of method which helps us to find step size, we call them in general line search method. Now let us generalize it. We have seen that this x1 equals x0 plus f prime by f double prime at x equals x0. That will take us to x1. Therefore, in general, we can write that this x at k plus 1th iteration is equal to xk plus f prime divided by f double prime x at x equals k. Now, if you recall the Newton-Raphson algorithm for root finding, when we have tried to find this fx equals 0, how did we find it? The algorithm was x at k plus 1 equals xk plus f by f prime x at xk. Now you see that they are very similar looking. Only thing that instead of f of f prime, now I have f prime by f double prime. So clearly here what we are doing, this is a root finding algorithm actually. What we are doing, we are actually finding the root of f prime x equals 0. The usual root finding algorithm we find the root of fx equals 0. This is the only difference. So you may be wondering that why we are discussing this once again. We are discussing this once again because this idea of picking a direction and picking a step size and then iteratively going toward the optimum point, this is an idea. It's a very, very general procedure, and this is the procedure we are going to use in multidimensional cases. So we are discussing the base case here, how this idea comes from Newton-Raphson method. And this family of methods, we'll call them this gradient-based optimization or gradient descent type methods, which are very, very popular in multidimensional unconstrained optimization. Now to take a look at our problem of finding the value of root over 2, we have discussed this problem can be framed as an optimization problem. If we find the minimum of this function fx equals x square minus 2 whole square, then that minimum should happen at root 2, and the value of that minimum should be 0. Why is so? We have discussed that before. Now we can use this Newton-Raphson algorithm to figure it out, and we need this f prime and f double prime. We have the fx here, so our f prime is simply the derivative of this. That will give us 4x x square minus 2, and then we need the double derivative that will give us 3x square minus 2. So now we can write a Python program. Here we are having this fp and fpp. This is f prime and f double prime. We are giving them as input in lambda function, and then we start with an initial guess. In this case we have taken an initial guess of 1. Then I enter the for loop. Here I am giving a correction with this initial guess. That correction is f prime divided by f double prime. This is my correction of this initial guess, and then I take it as this f prime x equals x minus dx. Now I print I and x. I stop where this dx, that means my step is very, very small. The output from this program, as you see that it takes up to 6 iterations only to give us a converged result. It's super fast and it takes only few iterations. Should have a minus here, so you can make this correction to have a minus here. Now you can see that how this method works. This is a gradient based method. It converges very rapidly, and this is the default type of method we'll use in multidimensional unconstrained optimization. Not necessarily Newton-Raphson there, but this similar philosophy we'll use it there. So now to summarize, we have discussed Newton-Raphson, which is a gradient based method, and this is the precursor of most modern optimization methods. It requires the function to be twice differentiable. If it is not so, we cannot use this method. It also requires a good initial guess. Of course, we didn't discuss that too much, but when we go far from this minimum point, then some of the assumptions that we have used, that f prime x at next step will be 0, that may not be a good approximation. That is why if we have a good initial guess, it is actually much better. It will definitely converge then, and if it converges, it will be blazing fast. It will be very accurate. So for your exercise, you use the method we have just described to minimize this function fx equals x square plus 54 by x. Compare this with analytical solution. Thank you. That's all for this lecture, and I'll see you in next class.